Part 6, Properties of Harmonic Resonance. Harmonic resonance, even in its simplest forms, exhibits some curious properties as a spatial computational system. Consider a simple resonant tube like a flute. When you blow a note in a flute, a pattern of standing waves emerges in the body of the flute at the same time as a sonorous tone, a harmonic tone, emerges. Here are the first through fifth harmonic shown here on a vibrating guitar string, but this could also be considered an amplitude function on the air pressure in the flute, which oscillates mostly in the middle for the first harmonic, and the second harmonic that has a high pressure, low pressure, alternating with low pressure, high pressure, third harmonic, high, low, high, alternating with low, high, low, and so on through the fourth and the fifth harmonics. The first harmonic is the dominant one. It's the one you principally hear. The higher harmonics are just ringing on that fundamental. So what this mechanism does is it automatically reifies every periodic subdivision of the tube simultaneously and in parallel. This is a truly magical process, the only physical system that defies entropy and creates order out of chaos. Now, the harmonics in a tube can be modulated or filtered by opening a hole like the holes in a flute. And what this does is it automatically damps any of the waves that have a high amplitude vibration right at the location of the hole. So if we look over here, the yellow here is the first harmonic, then the red is the third harmonic, and the pink is the sixth harmonic. And when you open a hole right here, all those harmonics are damped because the hole kind of short circuits the air pressure here and allows contact with the outside air. So this leaves, in this case, only the second harmonic in blue and the fourth harmonic in purple and the sixth harmonic. These are indeed the even harmonics. The damping creates a mirror symmetry out of the patterns in the tube. Now, if you open a second hole, say a 1/4 distance along the flute, then this will damp selectively those oscillations that have a high amplitude right here, in this case the second and the sixth harmonic, which leaves only the fourth harmonic left that is consistent with this input. Now, curiously, when you damp this quarter length of the tube, there's also a virtual damping that appears over here because it's the fourth harmonic. So any energy over here leaks out through the hole at the quarter distance. Here are some Chladni figures produced by bowing a steel plate with a violin blow while damping the plate with a touch of the finger. The patterns of standing waves are revealed by a sprinkling of salt or sand that settles along the nodes where vibrational pattern is minimal. Here's the Harvard Natural Science lecture demonstrations for Chladni plates, starring Daniel. Notice how he touches a plate to create a node. Here he's putting 2 points right next to each other. That creates a very high frequency harsh sound. The patterns on a square plate are constrained by the square shape of the plate. Where he bows it, it tends to form an antinode with periodic nodes in between where the salt or the sand collects. See how the touch of his thumb induces a node to form here. The damping touches with your finger are like the input to this system, and the harmonic resonance responds to the input. Here's Mary Waller from 1961. She developed a different way of making the plates resonate. She uses a piece of dry ice held in a pair of tweezers and presses it against the steel plate. Here is a plot of the many different patterns from Mary Waller's book that she managed to elicit from a square steel plate. The patterns on the upper left are lower frequency patterns, lower energy, and going down towards the lower right, they get higher and higher energy. These are harsh screeching sounds. Now, if you damp the plate, now this is just one plate. I was showing the many patterns on the plate. But if you take that one plate and you damp it at the upper left corner, you kill off all the patterns that are not that do not have a node in that upper left corner. So that leaves only the patterns shown here outlined in yellow that do have a node on the upper right. So by damping at this point, you selectively mute all of the patterns that are inconsistent with this input. If you touch the top center, again, this is the same plate, then you highlight all of the nodes all of the patterns that have a node at the top center. And if you touch both at the same time, you get selectively only those patterns that are consistent with both the damping on the upper left and on the lower right. This is an extraordinary system of pattern primitives based on symmetry, arranged in a hierarchical order based on pregnance. It does not just find the simplest pattern, it finds all of the patterns that are consistent with the given input. And it reifies all of them simultaneously and in parallel unless excluded by further inputs. The competition between alternative interpretations occurs by constructive and destructive interference between the competing reified standing waves. Part 7. What can you do with resonance?